Alright, so in this video we are going to be going over MergeSort. So we're going to start by thinking more about our n-squared algorithms that we've been going over in the last two videos, insertion sort and selection sort. One of the things that we learned is that when you have something that is n-squared, when you double a vector, for example, it takes 4 times as long, right? So an array of original size is up here, and this would be, half the size, right? So this vector up here is double one of the halves down here, right? So when you double a vector, it takes 4 times as much time, right, to run that algorithm. So the same would be true in the opposite way too, right? So if the full array takes 1, then if we have it, it should take 1/4, right? It's pretty interesting. So what does that mean? Well, we can either do an operation, on the full array, or we could split it into 2, and then we know that it would take half the time. So although n-squared sounds bad, you double something, it takes 4 times as much time. Is there something that we could do with this splitting, right? So it takes twice as long to sort the whole array as it does to split the array in half and sort each half. Is there some way that we can make use of this? Well, that's the whole idea of MergeSort. So let's first start by just the merge. So let's say that we could sort half. We know that that's cheaper. What could we do after we have 2 sorted halves? Okay, so here's 2 sorted arrays, and if we wanted to merge them into 1 sorted array, we could look at the first value in each of these arrays and compare them, and always take the smaller of the 2. So in this case it's going to be 1, and then we move to the next value. So in this case it's going to be 2, and then 3, and then 4, and then 5, 6, 7, 8, 9, and 10. So how expensive was that? We made a single comparison each time, and since we had n total elements, this algorithm runs in O of n time. So the merge algorithm takes 2 sorted lists and combines them into a single sorted list. As long as both lists are non-empty, you compare their first elements and you remove the smaller of the elements and append it to the output. Once one list is empty, you can add all the elements from the other list to the output. Now, we're saying the word remove, but keep in mind that removing an element in a vector is expensive. It takes O of n time. So you don't necessarily want to explicitly remove the elements, but this is just the general approach of how you want to move the elements around. And so you're going to want to think of a better way to do that. So you have this idea of this concept of merging, and so if we could have 2 sorted sublists and then merge them together, this is kind of coming together as a nice algorithm. So let's talk about how we could maybe split lists. So let's say we have this original list, and we just keep splitting it. We keep splitting it down until we're left with lists of 1, right? So we started off with the top list, we split it in half, we split each of those in half, we split each of those in half, and eventually at the bottom we have, I don't know how many elements, 1, 2, 3, 4, 5, 6, 7, 8. We have 16 elements, and they're all in their individual lists, so they each have 1 element in them. So a list with 1 element is sorted, right? So now we have 16 sorted lists. So the whole idea of MergeSort is you go backwards and you take these sorted lists and you merge them into lists that are less that are one bigger. So here we're moving each of those arrays of size 1, and we're merging them with another array of size 1 into a sorted list of size 2. Now we're merging our lists of 2 into lists of 4, and now we're merging our lists of 4 into lists of 8, and then we're merging our lists of 8 into a list of 16. And we end up ultimately with a sorted list at the top using all the original elements, right? And so what just happened as you went back up here is you applied that merge algorithm that we talked about at the beginning. Two sorted lists, you just take the first element, smaller of the first two, the smaller of the front of each of the lists, and you just keep doing that until both lists are empty. So as you can see, this is very recursive looking, right? And it is a recursive algorithm. So the recursive step is that you keep breaking the list in half, and then you recursively sort each part, and then you merge to combine them back into a single sorted list. And the base case for the recursive algorithm is an empty or single element that is already sorted, which I showed in the little demo. So this is what the code looks like, and this is a code that has the main function down here, and this is the recursive helper function, which is defined up here. The way that the recursion works is here's the base case that was discussed. If it's less than or equal to 1, so a single or empty list, then it's already sorted, so you return, so that's your base case. Otherwise, what you do is you split the list and you call it twice on each of the two halves of the list. And then after you split each list, and it's going to recursively go in, then you are going to merge on your way back out. And that is a little bit about MergeSort. So looking and analyzing and you're going to do a lot more with this algorithm, so we're going to leave it at that for now. But looking at this algorithm, it's a little bit harder to think about and analyze recursive algorithms for some people than iterative algorithms. So the past algorithms that we've analyzed this week are linear and binary search, which are both just like for loops, right? And so you can kind of see the loops, you can see where the ends are. And then, the sorting algorithms we looked at are nested for loops, so you can see that there's n squared there. But recursion gets a little bit more confusing to see what's happening, so you kind of have to draw it out. So the first question is this recursive call here is being called every time until the base case, which is until you have a single list. So the question is, how much work is being done at every recursive call? Well, we know that the merge is happening, right, at every recursive call, and we know that merge is on because merge requires you to move n items. So even when you're going from this level to this level, you're only moving 2 in each individual level, but you have it for all of the list that you're merging. And so that is just the same at every level. It's O of n. So how many levels are there? So each recursive call is going to cut the array size in half. And so you can see that you have n over 1 elements in the original array, and then you split it in half, so you have n over 2, then you have n over 4, n over 8, and so you can call each subarray the size of each subarray as n over 2k, right? So k is the number of layers, and so the original array has size n, and each subarray has size n over 2k. So the recursion stops when you're down to a single element. So the question is, what choice of k makes it so that you have reduced the size to 1, right? So n over 2k is the size of each subarray. So how many k's does it take in order for you to get down to size 1? Well, it takes log n. And it is log base 2 event. I think a lot of people, when they start looking at the log scale big O's, remember there's lots of log bases. It's log base 10, and that's it's log base 2, and that's because of the splitting in 2 on the way down. So that's where the log n base 2 comes from. So you have log n levels of recursion. You have on each level O n work. So the total work done is O n log n. And so that's how you can go through and analyze the recursive merge sort algorithm. And best case, worst case, and average case is easy for merge sort because it's all the same. It does the same thing no matter which one it is. So all cases are n log n. So you have worst, best, and average case are all the same. And so that is the big O of merge sort. And a quick aside, the merge sort algorithm was invented. It's a kind of funny way to say it, I guess, by John von Neumann. And it was invented in, it was just like, 1945 is when they came up with it. It was actually one of the first algorithms written for like a modern computer, where there was actually stored information on it. And so that's kind of a cool little tip about it. If you go read the Wikipedia page on von Neumann, you can read a little bit about it, and then it's also on the merge sort page too. But it's kind of interesting to read about it and how long it's been around. I always think that's really interesting if you think about computer science, or you actually can see the same thing in like math and physics and a lot of the sciences, is that a lot of times things are like theoretically discovered and done before they're useful. And like this was right on the cutting edge. It was like right when computers would even be able to do this. But a lot in computer science, was kind of like theorized before it was like able to be tested. And I think that's always really interesting. And so you think about everything that's going on right now in science and math and computer science, that people are theorizing of, but that's not possible yet. It's just really kind of cool. Kind of blows your mind. So that is it for merge sort.